Okay, here we have a centripetal motion problem. This is a force problem that's going to use ideas of Newton's laws. So in this particular problem, we have a bucket that is being swung in a vertical circle. So the bucket's being swung upside down. And the water is not going to spill out, and that's going to be the premise for parts A and B, and also for C, but we're going to extend the idea. And we're given a certain length for the string, and that's going to be defined as L. Okay, so the string has length L. All right. Okay, and that is going to be that's going to be our radius of rotation. So L is 1.60 meters, and it is our radius of rotation for purposes of centripetal acceleration and centripetal force. We also have the mass of the bucket and the mass of the water. So as far as that, we'll call those two different masses MB and MW. So essentially, the notion is that we have some water inside the bucket. We can kind of imagine how much it is. It's not relevant for the problem. But here inside, we have the mass of the water. So MW. Okay? But then we also have the mass of the bucket outside. Okay, so that's MB. Okay? And so those two values, MB and MW, so MB is given as 2.4 kilograms, and the bucket as, or the water as 4, MW as 4 kilograms. Okay. All right, and okay, which is equal to 4 liters of water because 1 liter of water weighs 1 kilogram. So part A asks us what is the minimum speed the bucket must be traveling at the top of the swing in order for the water to not spill. All right, so let's draw a free body diagram for part A. Okay, so what that's going to look like if we kind of highlight our bucket here. All right, so here is our bucket. We're going to have the handle of the bucket. All right, and then of course the string. Okay, like so. Okay. All right, so now let's think about the forces, let's consider first of all the acceleration. So since this object is going through circular motion, we know that the direction of centripetal acceleration is going to be towards the center of the circle. Okay. And so at the top of the swing, which we have, which is shown, I just drew, the centripetal acceleration will point down. Okay. So this is going to be the vector A sub c. Okay, but what about the forces? Okay, so the forces that we care about acting on the water are going to be the force of gravity and the normal force, because the idea is that we need the normal force to be 0. We need there to be no push for the water. Okay, so let's draw in our water. Okay, so here is our water, and getting to the forces, we have the force of gravity acting on the water, and again, the location of the gravitational force vector that I just drew isn't relevant to the problem, and I was not careful about where I drew it. I just put it where it fit. And then there's also the normal force. Okay, this is F sub n. Okay, that would be the bottom of the bucket pushing on the water. Okay. So we don't need the mass of the water. It's actually going to cancel out in this problem. But we have this idea. So we can say that in order for the water to not spill at the top, of the swing, the normal force needs to be 0. Okay, like so. All right. Okay, and so what that's going to look like, that would be just Fn of 0. Okay, so then if we take a look at what the forces will be then in the y direction, okay, and I'll draw the y direction, okay, that's the, well, positive y direction's up, so we'll define positive y is up, okay, and then we can also think of the radial direction, and the radial direction is down, okay, because it's all the radial direction always points towards the center of the circle, okay. But here we'll just think about the y direction because we are at the top, and that makes sense for thinking about water. So we have the mass of the water times gravity. That's Fg. Okay, so that's this force right here. And then we're going to have 0 because the normal force needs to be 0, and then that's going to equal mass times acceleration. So mass of the water again, and then specifically the centripetal acceleration. And this is just a really good demonstration of how Newton's second law and centripetal force work together, because here we have a situation where they all point in the same direction. So it may seem like that we can't have things balance out, but in reality, the gravitational force and the centripetal force, they're acting in the same direction, but they are balancing each other because they're one and the same. Right, so the centripetal force is not a separate force. It is just an inertia, a mass, times the centripetal acceleration. Okay, so let's then expand our expression here. So if we continue with it, then we can write mass of the water times g is then going to be the mass of the water, and then I'm going to rewrite the centripetal acceleration in its scalar form, which is just v squared over r, okay? But here, r is L, because that's our radius of rotation, okay? So then we can see right away, as I mentioned a minute ago, that the mass of the water is not needed. It cancels out. And so then when we actually solve for the velocity, it's just going to be the square root of GL, and that's just going to be the square root of 9.8 meters per second squared times 1.6 meters. Okay? All right, and so then what that's going to look like, that gives us a V minimum, right, because this is the minimum velocity that we have to be, that the bucket needs to be moving at in order for the water to not spill, of 3, well, let's plug in the number here. Okay, so let's take the square root, and we're going to have 9.8 and then multiply that by 1.6, and yep, so it's, if we're going to stick with, so all our values are given in 3 sig figs, and in this class we don't let acceleration affect the number of significant figures, so we should have 3 significant figures in our answer, so it should be 3.96. Okay, so 3.96 meters per second. Okay, that's the minimum and required velocity. Okay, so in part B, we're asked, what is the tension in the string when this minimum speed is achieved? Okay, so let's take a look at the things that we need to consider to answer that question. Okay, so we'll take our same bucket. Okay, so I've just copied over the same bucket here, and we're going to want to consider, instead of the water as our free body, we want to consider the bucket as the free body and then see how it acts on the string. Because before, the water was in contact with the bucket, which led to a normal force. And of course, we had a non-contact force, gravity, acting on the water, and then we had a centripetal acceleration, which creates this force, right? But again, a force that always shows up on the right-hand side of Newton's second law, right? Because this is the left-hand side, this is the net force, right? So when the net forces are these. The right-hand side, the MA side, that's the only place where you see centripetal force, okay? But now, in part B, we're not interested in the water being our free body. So instead, we're going to have the free body be the bucket, which is then, so we'll have some different considerations, okay? So So let's draw in the forces that are acting on the bucket. So it's going to be the force of gravity. And again, I'm not drawing it in any particular location. I'll just draw it over here. Okay, so this would be the force of gravity acting on the bucket. And then the tension. Okay. So before we started in part A, we started with the assumption. We said, okay, you know, what must be the speed with the notion that the normal force is 0? But does that also mean that the tension is 0? So let's just naively plug in the velocity we saw for part A and see what that gives us for tension. Okay, so then we'd have the net force in the y direction. Okay, this time acting on the bucket, and we have tension or negative tension. Okay, and then also actually one thing that wasn't particularly clear up above is I wrote that positive y pointed upwards, but then I made all of my vectors that pointed down. I didn't give them that negative direction, so we should put that in here. And the reason that I was not as careful about that as I should have been is because it immediately cancels out. So we can think of the negatives canceling out in the first step up above. Okay, I'll do the same thing here. I'll stick with having everything, since all the forces point down, we will think of them as negative, which is a good idea. Okay, minus MAC. Now, had we defined our forces instead, and so if we could have said instead F net in the radial direction, then it would have just been T plus FG equals MAC, because the radial direction is positive because it points towards the center. But we will stick with Y. Okay. So what does that look like? Well, let's go ahead and solve for T. Okay, so we can basically the negatives cancel out in a similar manner, and we're going to have M. Oh, and by the way, this should be mass of so the free body. Okay. Now also I want to be careful here because I kept saying, okay, well, these are the forces that are acting on the bucket, right? The tension force, gravitational force. But the water's inside the bucket, right? So the water is contributing to the mass, the inertia of the bucket, and thus to the tension and the gravitational force, right? Because it very much is inside of it. And so we can't, so really it's not the mass of the bucket, but it's actually the total mass that is in this consideration, okay? And that's just the mass of the bucket plus, so the given mass of the bucket plus the given mass of the water. So M total, okay? And then, right, that would factor out of V squared over L minus G, okay? All I've done here is just the algebra from the line above, okay? And then if we plug in the values, okay, so we're going to want to plug in M total should be the sum of 4 and 2.4 kilograms, which is 6.4 kilograms. So it would be 6.4 kilograms. The velocity that we solved for, 3.96 meters per second. Quantity squared divided by 1.6 meters minus 9.8 meters per second squared. Okay? So let's see what we get then. What do we get for the tension? Okay, so we'll go ahead and plug that in here. So we've got 6, okay, so 6.4, and then multiplied, so open the parentheses, 3.96. I'm going to get the value from above, so we don't have any worry about rounding. We're going to square that, all right, and then divide by 1.6, all right, and then minus 9.8, and then close parentheses. All right. All right, so we get 1.125 times 10 to the negative 8, okay? So because of some rounding in the device itself, we did use all the same values. We carried the number over. And you may see some difference between calculators, but the point is that we do have 0, right? So this is just the calculator not giving us exactly 0, but we're giving something that is effectively 0. And theoretically, the answer should be 0 because we'll say it makes sense that if the normal force is 0, so too is the tension equal to 0. Okay? So move that line over so we can see it. Okay? So in this, these forces that point in the radial direction, if we're going just fast enough to zero one of them out, then we're going to be zeroing both of them out. Because whether we think of the free body as the bucket plus the water, or we think of the free body as just the water, either the normal force or the tension is in fact the force that creates the centripetal force. And if we're trying to balance that force with the gravitational force in order to create this equilibrium where things are neither moving towards the positive radial direction nor towards the negative radial direction, they're just at that equilibrium. And in this case, since it's vertical, just at that one moment in time they're in equilibrium. Well, then they both have to be 0 because they're playing the same role, whether it's called tension or the normal force. All right, so in the last one, we're going to mix things up a little bit, or part C, I should say. We're going to mix it up a little bit, and we're going to have the bucket go faster in order for there to be a non-zero normal force. Okay, so this would be a case where basically you're not just spinning it just barely fast enough for the water to not fall out, but you want to err on the side of caution and spin it plenty fast. But in that case, the water will push against the bottom. Which would still make for a successful spin. It wouldn't spill, but then if it pushes on the bottom of the bucket, then the bucket pushes back. Okay, so let's tackle part C. Okay, so in this case, the normal force is given, or desired as 20 newtons. All right, so let's set up then our forces in the y direction. Okay, so then we're going to have at net y is going to be negative gravitational force. Okay, and I'll span that out because that's going to be the water, because we're looking back at the normal force here, minus the normal force, non-zero, and then equal to negative MAC. Okay. All right, so then what this is going to look like is we're going to have mass of the water times g plus 20 newtons. I just canceled all the negatives. Is going to equal then the mass of the water times the velocity squared divided by L. Okay. Notice the mass of the water does not cancel out this time because we have this fixed value on the normal force, and so since it doesn't have symbolically the mw in it, it's not in every term. Okay, so then we're going to solve for v. Okay, and then it's just going to be gr plus 20 newtons divided by the mass of the water. Okay. And I'll show those values in the calculator, and then we'll put the answer in. Okay, so what that would look like, so if we open up the square root, all right, okay, and so then we have 9.8, oh, and this shouldn't be an R, it should be an L, right, because that's our letter for the radius of rotation. Okay, so multiplied by 1.6. All right, like so. And then a plus. All right, plus. And then 20 divided by the mass of the water, which is, let's see, it was 2.4, I believe, right? So, yep, 2.4. Okay, so divided by 2.4. All right, so 9.8 times 1.6 plus 20 divided by 2.4 kilograms. That's giving me 4.90. Okay, meters per second. All right, so a little bit faster than before. And that's exactly what we'd expect, okay? Because absolutely it should be faster than our 3.96. And if we were to solve for the tension force, we would find that the tension force is also equal to so I should say not equal to 4.9 meters per second. That's not the units of tension, but I will just say here, this means that the tension force is equal to 20 newtons as well. Okay, because just as before, when the normal force was equal to 0, so was the tension. Likewise, if we were to shift our point of view from the water to the bucket with the water inside, we would find that the tension was 20 newtons at this speed of 4.9 meters per second. Okay, and you can check that yourself. Thank you.